Right. So, Newton's three laws, we can write them down.
Why Newton's third law? Three laws.
What? Say again?
Why third law? Why not third law?
No, we're going to look at the three laws, first, second, and third. Yeah, we're looking at all of them.
Oh, okay.
Yeah, because last time we only did Newton's second law.
Yeah.
What's wrong?
I wanted to be sure, is it like 3 laws of force or 3 laws of motion?
You could say Newton's three laws of motion. Well, it might affect if you're trying to find stuff online, like notes. So, Newton's three laws. You got that? Yeah? Okay. So, Newton's first law, I wonder if anybody knows it.
Every action has a reaction.
Not that one. Not that one. Yeah, it is, yeah. You think you know it, Tommy?
What is the reason why change the motion of the object?
Yeah, pretty close. Yeah. Not 100%, but pretty close. Yeah.
An object remains in its position
Yeah.
only if I can only move from its position by an external force.
Yeah, you pretty much have got it. There's only one situation you've left out there. So it's not only if it's stationary.
So I can also change the speed.
Yeah, but there's two situations, which you'll see now. Newton's first law says that if a body is at rest, what do you think? It will remain at rest, or if it's in motion, it moves at uniform velocity, unless or until it's acted on by a resultant force. So this is what you were saying, Dami. It will stay at rest unless a force acts on it. And Kayhan, this is what you were saying. A force is what causes it to change. So we need to put the two together. It will be at rest or a uniform motion unless it's acted upon by a resultant force. Oh yes, happy Chinese New Year Eve. Yeah.
Teacher, is this a lunar New Year or Chinese New Year?
Lunar, is it?
Yeah,
No.
lunar, yeah.
So what's
In the
the
4 o'clock.
Because
Oh, at 4 o'clock.
Yeah, in the 4 o'clock.
I
it's
think
New Year.
the lunar one uses sunset as
because
the end of the day, is it? You said at 4 o'clock. Or is that
4 o'clock is in Chinese time. The time in China.
China local time is 12 o'clock.
so you're going to celebrate here at 4 o'clock then to be at the same time as China then? Yeah, okay.
So what is happening in China? Is it
New Year.
New Year, yeah.
No,
New
the
Year.
rats. Don't you know?
Late New Year.
as in
because I think this day all of the Asia have a holiday. Oh, it's a celebrate.
Oh, okay. It's a big holiday then.
It's
Yes,
not just in the China. I think-
Really?
Yeah.
Oh, I always thought it was just in China.
Yeah,
So
it's
today
the
is meant to
biggest
be called
festival.
Because in Vietnam.
Yeah, we're not in China now, man.
Because in Vietnam, in Japan, and Korea also.
Really?
it's
I didn't know that. Okay.
Japan's New Year is 1st of January.
But they still celebrate.
Yeah.
Yeah, okay,
celebrate, but not.
Well, I heard there's some little celebration tomorrow here, isn't there? In the city centre.
Yeah,
just-
because time is different.
Yeah. Yeah.
I just want to be sure what exactly are they celebrating?
Their New Year on their calendar.
On Chinese calendar.
Okay, so January has 32 more, right? 32.
It's like Chinese calendar is like different between this calendar, it's like different than every year. Yeah, using the Chinese calendar, I don't know how they explain.
Okay, the Chinese has his own calendar.
So Chinese calendar tomorrow is January 1st.
Yeah,
So
yeah,
people are
yeah.
saying
Chinese calendar.
Wait,
It's
so
like an
That's
old
like
kind of-
2019.
Tommy, wait, hang on. You're studying physics. I think this is an easy idea to understand. That other people can have different calendars.
okay, but I want to understand. Have they been in 2019 since yesterday?
Yes.
No, it's probably, do in China you still measure the year as 2019 or is it a different year?
It's like Chinese calendar.
Yeah,
It's 2019.
it's still 2019.
And then tomorrow is 2020.
But the date
Yeah,
is
okay.
different.
Oh, but then tomorrow is 2020
Yeah.
then.
So we
Okay.
can still shout Happy New Year. Wow.
Yes, yes, we can still celebrate Happy New Year with them. Yeah. All right. Now, next one, Newton's second law. You all have that now? Yeah. Here's an example first, though, of Newton's first law in motion. Now, it's not 100% accurate, but it gives you the idea. So, an object will remain at rest unless acted on by an unbalanced force, or a resultant force, or a net force, whatever you want to call it. And then, here, an object will move at constant speed unless acted on by a force. Now, in real life, there is a force already on this, isn't there? What force is on this? Air friction is one, and what else? Gravity. So, like, in Newton's first law, it's very difficult to find a situation when there isn't actually a force when it's moving. It may be in deep space or something like this, you know. But this just gives you the idea of Newton's first law. Okay? Right, now, Newton's second law. You already know this one, because we did this one. What is it? Yeah, F equals ma. But how can we put that into a sentence? Force equals, yeah? Yeah, that will do. But we'd say force is the product of mass and acceleration. Got that? Yeah? Yeah? Of the three laws, this is probably the most important one. This is why it got its own lesson. Yeah. Okay, continue. Yeah. So, F equals ma. Newton's third law now, Marwan, you said it earlier. What is it?
Every
Yeah.
action has reaction.
Nearly, you left out a little word I would have liked before reaction. Every action has a... That's it. Every action has an equal and opposite reaction.
Newton must have been in Luna.
It must have been a what?
They are friends. It's always on that trade before.
Okay. So this law basically says that when you have a force, there must be some kind of reaction to the force. So if I apply the force to my book here, it has to do something. Okay? Even when it doesn't look like it. So, for example, here, if I apply a force, then the reaction is the change in the shape. Okay? Or if I apply the force, I could make it move. But there has to be a reaction of some kind. You understand? Yeah? Here's a simple, very simple example. Air is pushed out the back of the balloon. That's the action. And then the reaction here is the balloon is pushed forward. Yeah? This is a nice example of Newton's third law of action and reaction. Now there's many, many examples. Okay, continue.
Sorry.
Yeah.
Which sentence?
One sec, yeah?
Sorry, let's speak to where exactly is the action?
The action is the air coming out the back. Now, I'm not...
What is forcing the air out?
pressure difference. So the pressure inside the balloon is high. and pressure outside here is low, and the air is trying to equalize the pressure, so it will leave out.
That's fine.
Oh, he knows that. I mean, he's not an idiot. He's asking me what is the cause, and the cause is a difference in air pressure. Yeah. Okay, you got that? Continue?
Yeah.
Yeah. Right. So, here's an example of Newton's third law, but with forces. So, if I was to put something on the table, we all know that gravitational forces are pulling it down. A gravitational force is pulling it down. However, according to Newton's first law, if there's a force applied, it should be moving. Obviously, it's not moving. So the only way that that can be true is if there's another force acting opposite but equal in size. And we call this force here the reaction force, or the normal reaction force. The reaction force is the force provided by the reacting object. So it's like a support, a holding force, a carrying force. You know what I mean? But it doesn't have to be on a table. If you look here, if I push against the wall, obviously the wall doesn't move because the wall is reacting back, providing a reaction force. Okay? If my force was greater than the reaction force, what would happen? The wall would break. I sometimes do this. But the other situation isn't really possible. What if the reaction force was greater than my force? What would be happening? Yeah, the wall would be coming out at me, which obviously walls don't do. So reaction forces are always less than or equal to this force here. So if you want to think about it like this, if you have a wall here and you're pushing against the wall with a force F, the wall then pushes back with a reaction R. The R is usually equal to F. The R can be less than or equal to F, but we can never really have this. Now we can have it in some situations, okay? In some cases this can happen, but not really with a wall though. Yeah? Yeah, I was also thinking of, well, you know, we'll actually look at examples later, but if I had, no, I'll show you. Like, suppose I have this here. So this is the ground, and I put this on top of it, okay? There's a reaction force here, and then there's the weight here, okay? But if I move this up, then what's happening for the bulk is this reaction force becomes bigger than the weight, and so it moves up. Okay, and likewise, if I was then to suddenly remove this, then what would happen to the reaction force? It becomes zero, and so then it falls then. Okay. So what I need you to do is to write and draw this, please. Have you got that? Yeah, you got that? Yeah. Okay, continue. Okay. It's only one sentence. And you too, Marwan.
No, because my pen is.
Okay. Go.
Yeah.
Okay. Right. Here's a very simple example I want you to do. A block of 20 kilograms is on rest at the top of a table. What is the reaction force? So here it must equal the weight. So that would make it equal to 20 G, which would be 19.62 newtons. Fine? there's no need to specify the sign here. In the diagram, it's clear that when you say reaction force is 19.62, you mean it's the opposite to the weight. And actually, because the weight is, if anything was to be negative, it'd be the weight. So, okay, continue.
Sorry,
Yeah.
can you just say something? Can you just say it again?
Yeah, the reaction force has to equal the weight. They cancel each other. Yeah, 19.62. Oh, sorry, it's not 19.62. It's 196.2. What's 20G? 20 times 9.81. What's that? 196.2
yeah.
newtons. Yeah. You're looking confused at me.
Oh, you're calculating the force.
Yeah, the weight.
Oh, okay.
Yeah.
I thought you said that the force was equal to you, so I was confused.
It's okay? Alright, let's continue. Now, so this one you don't really need to write down, but this one is more. So, a block of 200 kilograms is at rest at the top of the table. A man tries to lift the block up vertically by using a rope. He pulls with a force of 1,000 newtons, but the block doesn't move. So obviously 1,000 newtons is not enough force to lift the block. What is the reaction force? So I'll give you a minute to try this. I recommend you draw the picture. There are 3 forces acting on the block. What are they? The weight, gravity, yeah, weight, gravity, yeah. The reaction force and the tension. Okay, give this a try. See what you can do. You got it? Yeah. Got it, yeah. People are you have it, yeah. I'll draw it. Here's the ground, here's the block. What did I say? 200 kilograms, wasn't it? Now, there are 3 forces here. There's going to be the reaction from the table, but he's also pulling it up with 1,000 newtons. And then, of course, there's the weight, which is 200 G newtons. Is the block moving? No. Newton's first law tells us they all must balance. There must be no force on this. So you have 1,000 plus or equals 1962. Is that 1962?
Yeah.
Yeah. So that means or is 1960. 3 significant figures. Newtons.
No.
No, of course not. Sorry.
Nine.
I know. Or is 962
Yeah.
newtons.
No, so
Yeah, it's okay. Okay? Yeah. Now, let's see next. Same story as before, except one small change. There's an angle that the rope is at. Is at 45 degrees. So what I'll do is I'll draw this for you so you can answer it. Here's the ground. Here's the block. And here's the rope pulling the block. And this is at an angle of 45 degrees. And this is 1,000 newtons again. And this is 200 kilograms. Yep. So once again, I'm asking you for what is the reaction force here. Okay, try that for a minute. Oh, is the block moving this time? Yeah, the block is moving. In the question I said the block is being dragged across the ground. So the block is moving along the ground. But it's not moving in the air. It's just being slid across the ground.
So it's moved.
It is moving along the ground.
Okay.
Yeah. You got this? You think you got it? No? Impossible? I'll give you a little hint, Dammy, to start you off. You should resolve. You got an answer, me?
Yeah.
Yeah. What answer did you get?
One,
The reaction.
the reaction is 1040
1040?
for 462.
And what did you get, Abdul Rahman?
1,250.
Ooh, that's a bit different.
1,254.9.
Ooh, maybe you should check that, me. Well, let's have a look. Guys, Dammy, we're going to have a look here.
I read wrong.
Oh.
450 is more half hour.
Okay, that's okay. We all make mistakes. That's fine, yeah. This one here is, how big is this component? 1,000 costs 45. And how big is the other one? 1,000 sine 45. So, and there's also a reaction and there's also a weight. So, reaction plus 1,000 sine 45 equals 200 G. So if I just take that to the other side, that's 1,000 sine 45 is over root 2. So if you put that in on the calculator, what do you get? 1, 2,
554.
5, 4.
0.9.
So like this.
Yeah.
5,
5, 5, 5, 5.
So be 6 then? 1, 2, 6, 0?
1, 2, 5, 4.
1255.
1, 2, 5, 5. 1, 2, 5, yeah.
Point. Yeah, but I want.
Actually, it's 1254.9.
Okay, good. So it's 1250.
1, 2, 5, 4.
1,254.
Yeah, but I need to have 3 significant figures.
Oh, yeah.
Oh,
So what is that? 1,250?
4.
No, 50 then.
54.9.
Yeah, so 50 then. If I want 3 significant figures. 1, 2, 3.
Okay.
Yeah.
Yes.
Yeah. 1249 point.
9.
Sorry.
1254.
1254.89. Okay, good. So 1, 2, 5, and this stays at 5 because that's a 4. Yeah. So 1, 2, 5. Yeah, so that's the answer. 1250. What's wrong, Ning? You look so sad with this. It's okay. In physics class, we must give the answer to 3 SF. Yeah. Yeah.
Where is 1,000?
1,000 is only one.
1,000 is one significant figure. Okay, look. 1,000. That's 1 SF.
Yeah.
1,300. That's 2 SF. 1,250. That's 3 SF. And then 1,255.
4.
That's 4 SF.
So if 1, 2, 5, 5, how to do?
Yeah, so what you do, 1, 2, 5. This is 5 because the next one's 8. So it makes it round up.
If
1260.
Oh, if we do one more?
Sorry, he's asking how to round it 1255 to 3 significant digit.
You want this to 3 significant figures? Okay, that'd be 1260. Yeah.
Well, but I think it may be a lot of difference between the real.
so if we answer is 1,250.
Yes.
So no, 1,256, or I must write to the 1,260, right?
No, you must write 1,250 for this question.
Yeah.
Yeah. But But if your calculation, let's say you got a calculation of 1255, for example, in the exam, what would you give the answer here as? Not 1255, but 1260
Okay.
in the exam.
Okay.
Yeah. The answer must be 3 significant figures.
Okay.
Is that okay?
Yeah.
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 I hope so. Okay, do you need to write this down?
Yeah.
Do we need to write this down or continue? Continue?
Continue.
A block of mass 73 kilograms is rest on a rough tabletop. A man is dragging the block behind him with a rope, and again the block makes an angle of 45 degrees, and again the force is 1,000 newtons. The block moves at a constant speed. Now, in this question, there's an extra force called friction or drag. So here's the ground. Here's the block. This is 73 kilograms. He pulls here with 1,000 newtons, angle 45, and there's a friction here. There's also a reaction, and there's also the weight. Okay? Do you have the picture clear in your mind? Okay, can I go back to the question?
Yep.
Yeah. So, try this first. I want the friction force and then the reaction force. Yeah? You got both answers? Ming? Yeah? Peter? What did you get for friction? 7? Yeah. 707, yeah. And reaction? 707 as well?
No, 9. 9.1.
Oh, the same as the passport. Okay. Right. So, what is to be done first is to resolve this and this. So this is 1,000 cos 45 and 1,000 sine 45. So what is that? Is that 707 point
0.1, I think.
something like this? 707.1. Now, it's important to know that this is moving at a constant speed. And so Newton's first law says if it's moving at constant speed, there's no force. So that means that the friction must equal 707.1, which is 707 newtons. Okay? And likewise, Newton's first law tells us that the reaction plus 707.1 must equal the weight, which is 73 times 9.81.
Yeah.
So what do we get for the ore here?
Going over
What is it?
9.02.
9.02 newtons. Yeah? This is actually a small reaction force, which means with a few extra newtons, the block would be lifted off the ground. 9.0 is not 9.0? 03, is it?
023.
No, it's like use 707.1, not 707.
Oh yeah, I use 707.1. Oh, you need to use 707.1. So if you use 707.1, what do you get?
It's like 9.0.
03. Okay. Do you need to write that down? How would we calculate the acceleration? Well, we can't, because there is no acceleration. It's constant. Yeah. And why is the reaction here? This is because of Newton's third law. Yeah. Okay, continue. Yeah. Right. Last one here is very tricky. A weighing scales really measures reaction rather than weight. I'll explain that here with the example. So when you have a weighing scales and it says your weight here, okay, first thing you might think, oh, it's measuring your weight being pushed onto it. But really what's happening is it's measuring the reaction. Now, that doesn't matter, does it? Because when you're standing on the weighing scales, will your reaction equal your weight? Yeah. So does it really matter that there's a difference? Not usually. It will matter though if the weighing scales is moving. Okay, so imagine the weighing scales is moving up. Which is bigger, the reaction or the weight? Reaction. And if the weighing scales is using the reaction force to calculate your weight, then will it think you're heavier or lighter? Heavier. And likewise, if you're going down on the weighing scales, which is bigger, the weight or the reaction? The weight. So the weighing scales will think you are lighter. The weighing scales is in a lift. A 1/2 kilogram book is placed on the weighing scales. The weighing scales is then lifted up with an acceleration of 1 meter per second squared. What would the reading on the weighing scales be? Will it say more than 1/2 kilogram or less than 1/2 kilogram? If it's being lifted up in the air. More. Calculate. So, I'll give you a few minutes to try and then I'll give you the answer. See if you can figure this out. It's quite interesting. Now, I'll give you a little hint. The weighing scales uses the formula W equals mg to give you the m. But the weighing scales is wrong in thinking what the W is. It was a good question. I'm seeing people thinking. Have you got an answer? You think so? What do you think you got?
0.551.
Sounds believable. Difficult? No. Right, let's have a look. So here's the weighing scales here. And the weighing scales is giving you the mass here. Now, will it be the right value? No, it will say a wrong value. Okay. The book is on this here, and there are two forces acting on the book. There's its weight, which is 0.5 G, 9.81, and then there's the reaction. And which is bigger here? The reaction. In fact, you can say F equals MA. F will be or minus 0.5 G equals 0.5 A, which is 1. So or will equal 0.5 times 9.81 plus 0.5. Yeah. And what's this here? 5.41 newtons. Now, how does the weighing scales calculate the mass? The weighing scales thinks it's not moving, right? So it will use the formula W equals or, which equals mg. So the weighing scales will say the mass is equal to the or divided by g. However, it will give the wrong value. What's wrong in this formula for the weighing scales? The weighing scales thinks the reaction is the same thing as the weight. Is it though? No. In fact, the reaction is bigger than the weight. But the weighing scales doesn't know that. So the weighing scales will think that the mass will be 5.41. It thinks this is the weight, divided by 9.81, which is 0.551 kilograms. So it says the book is an extra 50 grams. Yeah. Okay, that's a tricky one. Okay, do you need to write that down? You got that, Jeffrey? You didn't get it? Do you need to write it down? Did you write it down? Huh? Oh, you could do it? Okay. You have it, Kayhan? Yeah? A couple of people writing here. So I think if if it was going down, it'll probably say 0.45 roughly, or 449. Now you could test this out. I think some of those tablets or iPhones have weighing scales. You can download a weighing scale app and put a little weight on the screen and tell you the weight. I think some of those tablets have weighing scales apps. Yeah. Yeah. So you can put an object on the screen and it will tell you the weight.
I think it has no length.
Well, not like this,
Not too heavy.
Yeah.
Teacher, is this can check my weight?
No, I wouldn't recommend that. Anyways, if you want to, the next time you're in the elevator, you can put the phone on the ground, you can put a small weight on it, and you can see the weight change as you're going up and down the elevator, if you wanted to. Okay, did you write that down? Yeah. So, what I want you to do now, last 10 minutes, is to get a start on your homework, which will be the questions on this. Yeah, there's only 9 minutes left, Jeffrey. That's all I'm asking you to do. Do your homework for 9 minutes, please.